all.
And tell us about the moment, if you will. Well, first, before we get to that, tell us about being the Nobel Prize winner, a Nobel Prize winner.
Well, it's a complete change of life. Suddenly you're a famous person, and you have the world inviting you to do things and places to go and speeches to give. Everybody wants a little bit of your time. So then suddenly you have to be pretty selective about what you're going to do.
You're the first and only NASA scientist to win the Nobel Prize. Did you ever imagine this for yourself?
Well, people told me for a long time that we should win this prize. But I thought, well, I'm just not going to think about it. I could not imagine anything about what it would really be like.
We're going to show the unveiling of the trophy. Tell us about how you must feel being NASA's first, if you will.
Well, to me, it's just, I'm the same guy that I always was, and now I have a new job to represent NASA and to explain what this prize is about, what it was that we did, why it's important, and how we accomplished it. So there's a story to tell. And
we'd certainly like to, we want to hear that story. But first, let's start at the beginning, if you will. Your background. You were born in Roanoke, Virginia, and but you didn't spend too much time there, is that right?
No, my parents moved away when I was about 1 year old, and they moved up to northern New Jersey, to Sussex County, which is a farm country, and there's a research station for Rutgers University up there for studying dairy cattle. So that was my father's job, to study dairy cattle. So I grew up on a research farm.
And what was the atmosphere like for you as a young boy?
Well, that was a very quiet place to be. Very isolated, far from the city. Every 2 weeks, the bookmobile from the county library would come around, and I'd get the science books to read.
And why science?
Well, I guess I was always interested in science. My dad was a scientist, and I've been thinking about science things ever since I was small. I took the opportunity when it came by.
Now, in the earlier event today, there was much discussion about your having conducted a lot of science experiments as a young boy under the kitchen table. You entered in a lot of science fairs. Can you tell us a little bit about that?
Yes. I was one of the few kids in my school that was much interested in science. So, but I was really interested. So I collected stones. I collected seashells. I collected plants, and eventually started to read books and think about how to make radios and telescopes. And the experiment under the kitchen table was a biology experiment to find out what about diets for rats. So we had 8 little baby rats that lived under the kitchen table. That's what it didn't tell you. And my mother was very patient with these 8 baby rats.
I would say she'd have to be.
Yes.
And how did that experiment work out?
Well, it was a good project. I learned the statistical analysis from my dad. And I learned that cornflakes is not a complete food.
And that, I imagine, is what all they ate at that point?
Well, we tried many different diets, and cornflakes was really not good for them. But dog food's quite good. Anyway, I don't eat either of them.
And how old were you at that time?
I was in high school, 9th grade.
And by then you knew that you were going to be a scientist?
I could pretty much tell.
And did you have at that point an inkling of what particular area of science you'd go into?
Well, I loved astronomy. I loved electronics. And I didn't know what the rest of science was because I hadn't been out of town.
And you finally did get out of town, then,
yeah.
right?
I went to college away from town. Went to Swarthmore College, which to me was a big school, but is actually small. And then I went to the really big school, to Berkeley, for graduate school. And then when I got there, I wanted to understand elementary particle physics. That was the great intellectual challenge in those days. But then things changed. Some physics turned up in astronomy and the discovery of the cosmic microwave background radiation. So my thesis project that I found was to work with a group on measuring the cosmic microwave background radiation. And this was when it had just been discovered.
But going back now to college, when you got to college, you knew it was going to be something with physics and astronomy?
Yeah, I did. I was very eager to learn as much as I could. I had been away to summer school already in physics, so I knew this was really exciting stuff.
And when you said the field started to open up at that point to background radiation, tell us about that, if you would.
Well, in '65, when I was an undergraduate, this radiation was discovered, and suddenly everybody had to go measure it. So by 1970, I was looking for a graduate school project to do to get a degree, and people were measuring. So, okay, well, even a graduate student can make a contribution to this, so that was my plan. So my thesis advisor had an idea which he had developed, and so we drew up a balloon payload, an instrument that would measure the brightness of the cosmic background radiation. So we got some graduate students, I was one of them, and we set to work to build this thing.
For a non-scientist, explain how you would go about doing that. What are the givens? And I guess there's a process of elimination, if you will, right?
Well, I guess the first thing is you have an idea that there's something worth measuring, and then you have to invent a way to go measure it. So we had tried already on the ground to measure this radiation, but the Earth's atmosphere kind of gets in the way. So have to get above the atmosphere. So the next step is a balloon. So now you have to learn how to do that. It's basically you have to build a satellite project on a string that hangs from a balloon. It's got to have radio control, and all the data comes back by radio. And it'll last for a few hours. So we decided we had to have a liquid helium tank to get the instrument cold, and that's what we built. And that apparatus is now in the Air and Space Museum.
That's great. I had a question, though. Why does it have to be cold?
It needs to be cold because the radiation from the Big Bang is pretty faint. And so if your apparatus is warm, it's brighter than the thing you're trying to measure. So that was the deal. Make it really cold.
And so this was really the germination of the COBE project.
That was the instrument. Although it didn't work well for my thesis project, my fellow graduate student made it work after I left. Nevertheless, it was the idea that said this is worth doing and got me thinking about the whole thing.
Why do that experiment? Is it just because it was something that somebody needed to do, or was there something more, if you excuse the expression, more cosmic?
Well, we had a problem in those days. Everybody that tried to measure this, or maybe I should say almost everybody, found that there was something the matter with this radiation. Everybody was measuring too much. So it's easy to imagine that the experiments just weren't right. So we had to go try harder. And so there were an awful lot of wrong measurements that said, well, how about some better measurements? So this was a learning process for students and faculty to figure out how to do better. And then when we got to the end of what you could do with the balloon payloads, then the step is, well, now you have to go into space. You've done everything you can do.
Now, before we get to there, why is this important? I guess, beyond the fact that we want to know, but...
Well, we sort of like, as human beings, to know how we got here. It seems to be built into us that we want to know this. So the question of the origin of humanity and how we got here from the beginning of the universe has been really a thrilling topic for people in general. And so it's got some religious aspects about it. People have been asking this question in church for many generations as well. So anyway, for us to have a chance to measure scientifically how did it all start and to check out the stories and see if it's really true, that's really exciting.
When COBE was first proposed, tell us about that. That's quite a process in and of itself.
COBE was proposed back in 1974. NASA announced an opportunity to propose satellite missions. This was just 5 years after the Apollo program had first landed on the moon. So what are we going to do? Well, NASA got 150 proposals for wonderful things to do, and 3 of them were about this cosmic background radiation. So a couple of years later, after some various studies had been done, NASA said, okay, we're going to form a science team to decide what really to do. And they said, okay, science team, you work with Goddard Space Flight Center. We will make a plan. We'll make a design. And at first it was going to be launched on the Delta rocket. But then that was the time when NASA said, okay, we're going to give up all the expendable rockets. We're going to build the space shuttle. So everybody figure out how to use the space shuttle. So we did that. We had to redesign the mission from the Delta rocket onto the space shuttle plan.
And how many years from start to when you actually launched? How long did that take?
15 years from the first concept to the launch day, which seems like a long time. On the other hand, we were working like crazy that whole time to make it happen. There's so much to do when you start off with a project that initially you think it can't be done. You don't have the technology ready, you don't have the team, you don't have the design, you don't have anything except the idea. So it takes something like 6 or 8 years usually to get from concept to design, and then a similar number of years to actually build something.
Now, you had a team of, what, almost 1,500 people?
About 1,500 people